Hi, welcome to the fourth video of the Vortrix Algebra series. This was an unscheduled video that I'm inserting, and this has to do with the epiphany that came over me last week. The end result of the epiphany is that determined that simply changing the sign convention of the Vortrix Algebra product can radically alter the behavior of the product. And so I've come to the conclusion that going forward, that the worst problem we're going to have going forward is that we have the wrong sign convention right now, and that all we'll need is a sign convention to get what we're going to need. So let me show you how this epiphany rolled out. What I'm going to do is I'm going to warp between four different aspects of videos you should have already seen before, and some things I know you haven't seen before. So from the last video, demonstrate the vector product has to be a matrix. Has to be. There's no other way to rotate a vector than with a matrix. But what I did say is that even though I know it is a matrix, I'm not 100% sure I have the right matrix yet. And so I was keeping my option. I have nothing that says what we have now is wrong. It seems to fit all the identities and everything seems to check out. Okay. So that's where we were at the end of the last video. When I was writing the video, but let me go back before I do that. Let me go back. Warp 2, I showed in the, where we had the all swim chat for the entire Patreon, I showed the derivation or the end. This is in the paper now that's available to everybody. This shows the derivation of using a theoretical pretonic field model and going through a time derivative in Vortrix Algebra, and we come up with this, which is very, 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 very close to all the new electromagnetism terms. The big discrepancy was that the signs were all wrong. Or not all of them wrong, at least two of them are wrong. So we have a sign. That's why I'm putting these in red. We have an issue with signs. At worst case, again, we have an issue with signs. And what I have never released before is in the development of Q-Algebra, I also came to the conclusion that the only thing that signs were the remaining thing that were unknown. And in Q-Algebra, it was a little different than Vortrix Algebra. In Q-Algebra, we used a multiplication table. And what I did is I wrote a computer program that was searched through all the different permutations of the possible signs. And this number up here is basically the binary representation of the signs. So if you put the signs 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 1, 1, 1, 1, 1, and you put those into a binary number, you get 64801. And that's how, there's 65,000 different permutations here. Okay, and so this number here is a representation of the ones in binary, of the signs in binary, of the negative signs in binary. The numbers here represent the dimension. So what this multiplication table is saying, if you do x times x, it goes to the x dimension, or something like, I don't remember, I think this was x, y, z, and this was the q dimension or something like that. And so even under Q-Algebra, I realized that I was getting down to the point that signs were the only unknown thing, and that there was multiple different solutions just by changing the signs. Q-Algebra was abandoned because of the Q continuum was ambiguous according to the 17th rule, so I had to do something with that. So that's why Q-Algebra was abandoned in favor of Vortrix Algebra, which does not have the ambiguous dimension, but we're still at the same point where it is going to be a sign convention that's going to be the final decider of what the final Vortrix is going to be. Okay, and then the epiphany started when I was going to start the derivation of how to derive the matrix for Vortrix Algebra. And one of the things that I remembered is I made an assumption that because the dot product is the same for legacy vectors, it's the same for geometric algebra, and essentially it's the same for Vortrix algebra, but we didn't know that at the time because we're developing Vortrix algebra. And this is what it looks like. It's basically a scalar. In all three cases, it's a scalar. It's a scalar matrix here. Okay, even in Q-Algebra, the dot product is the same thing. Okay, and then so when I was doing the video to show the derivation, it dawned on me, how do I know the dot product is right? Okay, because the assumption that the dot product is correct is paramount to the derivation of the present Vortrix matrix solution. And the reason why is because we used the square vector. The square vector is a vector multiplied by itself, which the only part of the product that expresses itself is the dot product, and that works out to be a simple scalar of amplitude of the vector squared. And then we do this thing, and then what we do the same thing like they do in complex math. We multiply the top and bottom by c, and because this is a square vector, it turns into a scalar, and then we can reduce the entire derivation of Vortrix algebra to a triple product. We're going to cover this more in the next video, but the question is, what if the square vector doesn't come out to a scalar? What if it comes out to something else? And so the question we have to ask, is there a different meaning to the square vector? And actually, complex numbers have a different meaning. And if we actually do a complex number solution and put that into a matrix, okay, this is what it would look like. This is, in other words, if you do the triple product using complex numbers and you arrange all those, that would be an equivalent Vortrix matrix. This is the way that complex multiply would come out. Okay, and again, the only difference between the 2D Vortrix one that we're doing now and the similar one derived using complex numbers, the only difference are the signs. All of the terms are in the exact same places. The only differences are the signs. Okay, and so here's where we show that any possible solution is available to Vortrix algebra just by changing the signs. And the signs make all the difference in the world. Because if we compare these different matrices applied to a square vector, okay, this is what the square vector looks like in legacy algebra, in geometric algebra, and the present solution for Vortrix algebra, and this is what a square vector looks like in complex numbers. And you can see this, a square vector in complex numbers is, just by the signs, is vastly different. Here it's a simple scalar. Here it's not a scalar. Here it's a vector. So you can see, for all this bull, and this is a wonderful dovetail with what we said before, that geometric algebra is not isomorphic complex numbers. Because a square vector in complex numbers is a vector. So there's no way you can say that geometric algebra is isomorphic, because in geometric algebra a square vector is a scalar. Okay, so there's more evidence that geometric algebra is a fraud. But this is beautiful because just by changing the signs of the product, we can get a Vortrix algebra solution that mimics the behavior identically, isomorphic. I don't really care to call it that, but we can get this, we can make Vortrix algebra just by changing the signs. We get a solution that mimics the behavior of complex numbers wonderfully. But here's an interesting thing that blows my mind. If you take complex divide and make a matrix out of it, you get a matrix that has similar behavior to our Vortrix multiply, except for the little scalar over here, which is blowing my mind. And it's making me wonder, because in complex numbers now you have a different thing for a multiply and a divide, which is quite interesting, I have to say. In Vortrix algebra, your multiply and divide look almost the same, except you have one of these guys on the divide. But your matrix almost looks the same. So that's causing me some interesting, okay, we've got something else. We have an anomaly. We have a way now to go forward. We have identified that all we have to do is change signs, and we can change up what the result of the Vortrix solution is. Okay, so this is wonderful. But here's an interesting thing. If we generate the plane rotation operator, remember this was our answer to the complex operator, which geometric algebra calls the pseudoscalar. Okay, we use the unit direction in x, multiply the unit direction vector in y, and when we do that with Vortrix algebra, we get this, which turns out to be a value that represents the square root of -1 that isn't complex. Okay, and if we put that same value into the complex matrix that we showed you here, okay, we also get the same answer. Interesting. But here's what tells me maybe Vortrix algebra is right and complex numbers are wrong. Because if I juxtapose the vectors, I get the correct second root. There should be two roots to a square root. This is the second root, but complex numbers doesn't give you the second root. You end up getting the same answer again. You don't get the second root from complex numbers. Because in complex numbers, just by changing the signs, your multiply is no longer commutative. It's commutative. In other words, if you swap your vectors in Vortrix algebra, it changes the value of the results. Where in complex numbers, you can change the order of multiply and it doesn't change the result. Okay, that says to me complex numbers are still ambiguous and they're not complete either. So we're not saying here, because of this, we're saying complex numbers probably not the right solution either. So, you know, we still have a little bit of work to go. And you can see just by changing the signs, if we compare the properties of the complex answers to the Vortrix answers, you know, one's commutative, one's anti-commutative. One can get one of the plane rotation operators, the other one gets both. In a square vector in complex number results in the angle, the output, it results in a vector with the square magnitude but twice the angle of A, where a square vector in Vortrix algebra has same magnitude of a square, you know, A squared, but it comes out as a scalar, has no direction. Okay, and the differences between multiplication and division, you can read that on your own. It's amazing, just by changing the signs, we have a totally different animal. So again, bottom line, I'm convinced that the only possible remaining issue with Vortrix algebra may be the appropriate sign convention we must choose. And what's forming in my brain is a possible search engine where we have a computer for loop that permutates through each sign possible convention, of which there's 65,000. But we could probably pare that down with a little bit of logic. And then we run each one of these permutations over each of the experiments. We'll pick a suite of experiments that will use a particular sign permutation on and compute the results of an experiment and see how those results agree with real experimental results. And what we do is then arrange all the different sign conventions in the order of least error in predicting the output of the experimental results. And then we can probably narrow it down to which one is best mimics nature. I think I'm going to begin this effort soon, but this will probably not be a product that's something that's not going to be ready for a while, because it's a lot of work. Okay. Again, the final frontier is determining which sign convention best matches. This is not, these numbers aren't right. But anyway. So what we're going to do in the next video is, again, we're going to demonstrate the exquisitely simple derivation of the Vortrix product using simple arithmetic. And now this next video will definitely start the 4 patron-only videos. But what we're going to do also is we're going to show you how to derive the complex equivalent using complex numbers and show how you can get the Vortrix matrix out of that, just to show you, to give you another way, another opportunity, another dimension of how to do something with Vortrix algebra. And that derivation is not part of the Vortrix algebra paper, so because I didn't think of it back then, so those people that are hoping to just read the paper to learn everything, you better become a Patreon subscriber, help out this effort, and you'll be able to see. Thank you. No more voodoo physics or imaginary math. Thank you.